Hi everyone, I'm Rachel Chen from Dartmouth College. Here I will present our work TanGo, exploring expressive tangible interactions on hand-mounted displays. This work was done when I was in Taiwan with a collaboration with Qi Huanjiang, Shuwen Xu, Jiyun Yang, Dayuan Huang, and Bingyu Chen. There are various handheld controllers for virtual reality, such as HTC Vive, Oculus Rift, Samsung Gear, and Leap Motion. Other than handheld controllers, there are input techniques where users manipulate the hand-mounted display. Google Cardboard enables binary input by simple mechanisms such as magnetic toggle and conductive tap, so that users don't have to carry handheld controllers. However, such mechanism can only support simple tasks such as point and select. They cannot be adapted to more complex applications in virtual reality. Previous research has explored HMD input. For example, Scratch VR extends Google Cardboard to enable different forms of input. Face Widgets places various physical widgets on the backside of the hand-mount display so that users can switch between input modes. Aside from the input techniques, haptic feedback on hand is also being explored in previous work. Rolling Stone is a prototype VR controller consisting of a ball-based sleep display, positioned under the user's fingertip to generate textures and force sensations. Haptic Revolver renders arbitrary textures, shapes, and interactive elements using reconfigurable wheels. Kinesthetic feedback on VR controllers has also been investigated. For example, Wolverine is a mobile wearable haptic device designed for simulating the grasping of rigid objects in virtual environment. And Drag On adapted the drag and mass distribution by air resistance to provide different haptic sensations. Thor's hammer and aeroplane both utilize propeller propulsion to generate ungrounded force feedback. However, such devices usually require large space and are tailored to some grounding device, therefore limiting mobility. Kinesthetic feedback has also been applied to different appliances, such as Squeeze Block, a mobile module that can generate different levels of spring force, and Frictio, a smart ring that provides resistive force output along with rotational input, and Arneo, an interactive chair that can restrict a user's motion by modulating the resistive force when actions are being carried out on the chair. Such kinesthetic feedbacks can enhance game experiences on these form factors and can also be used in everyday tasks such as notification. Inspired by these previous works, we proposed TanGo, an always available input modality on VR headset. TanGo enables sliding bimanual input coupled with resistive force output. The mechanisms in the TanGo prototype are covered by two shells, so users can grasp the device more easily. We also added a strap to fasten TanGo to the user's face, thereby reducing the disturbance when TanGo is manipulated. For each side of the prototype, there are 3 sliding mechanisms in the shell. Each of them moves in the X, Y, and Z axis respectively. Inspired by joysticks, we equip each axis with a spring return mechanism so the device can return to its original position when the user releases it. To provide resistive force feedback, brake systems are added to all axes. The brake system consists of a servo motor, a 3D printed gear, a 3D printing arm, a rubber brake pad, and a piece of belt covering the gear. By pushing the brake pad against or away from the slider, we can modulate the resistance on the sliding motion. TanGo can generate totally 6 force profiles. The first one is natural resistance, in which no additional force is applied by brake system. The overall resistive force that users feel is from the sliding mechanism and the spring return mechanism. And strong resistance. Users can push TanGo while feeling a resistive force stronger than natural resistance. So you can see in the video the user can still move TanGo but more slowly. Compared to above force profiles, lock has the highest resistance, which can stop the user from moving certain degrees of freedom. So you can see the shells was locked after user releases it. As to ramp up, the resistive force starts from natural resistance and increases linearly with the displacement of the slider. So you can see the user in the video is kind of being hindered due to the growing resistance. The working principle of ramp down is similar to ramp up, but the resistive force starts from strong resistance and decreases linearly to natural resistance. The resistance level of click alternates between natural resistance and lock to simulate the feeling of sliding through one or multiple bumps. We have 3 applications for demonstrating TanGo. The first one is a tank game. In the tank game, users can push TanGo forward to drive the tank forward, and also turn a tank using cross gestures. They can also aim or fire using other gestures. The second one is an exploration game. In the exploration game, users can pick up the key by opening their hands, do a cross gesture to unlock the door, then open and close the door using other gestures. The last one is an AR demonstration. Users can move a paper code around the desk with one hand and enter gesture command with another hand. Different gestures can have different functions such as create, delete, switch object, scale up, or copy and paste, and scale down. We conducted a preliminary user study on 5 participants to understand the experience of using TanGo in the proposed applications. Some users reported that TanGo cannot stay firmly even when the strap is applied. This is mainly because of the great amount of force applied to the device when there is a resistive force feedback. The resistive force of ramp up and ramp down changes discretely with the displacement instead of changing linearly as previous figures suggest. Some users complained that the resistive forces are so strong that they cannot use the device normally, while others said the profiles are not discernible from each other, such as ramp up and ramp down. One of our users said this controller can be applied to different things that require 3D input, such as drone navigation, which is much more intuitive than joystick controller. For the limitation and the future work, we currently use slide potentiometer for position sensing. Due to the limited resolution, the brake system cannot accurately respond to user input. The size of the slide potentiometer also makes it hard to reduce the size of the device. We will use smaller sensors with higher resolution in future implementation. Comfort is also an issue. Some resistive force profiles are so strong that they undermine the user's experience. The design of force profiles should be carefully chosen in the future work. The ergonomics of the strap can be improved, and the weight of the device can be further reduced if we use smaller sensors. Third, we did not conduct a formal evaluation of the TanGo prototype. Evaluations of the time interval between profile changes, the success rate of users identifying profiles, quantitative ratings on each interaction, and an acceptable range of resistive force can be included in the future work. In summary, the contributions of this work are the concept of providing both input and haptic output on head-mount displays, and the implementation of TanGo, a proof of concept prototype, and a set of applications to demonstrate that concept, and the preliminary feedback of TanGo from 5 participants. Thanks for your listening, and if you have any questions, please feel free to ask. Thank you.